So here we have the question of whether or not reaction is exothermic or endothermic, and how can we calculate whether it's exothermic or endothermic. It's not that difficult, but we need to know what bonds were broken, what bonds were formed, and how much energy did it take to either break or form those bonds. The way you determine how much energy it took to break a bond or to make a bond is here in this bond strength table. You can read this across this way. So if I wanted to know how much energy it took to break an H, a hydrogen, phosphorus bond, I would go here, here's hydrogen, I go across to here, here's phosphorus. So it's 77 kilocalories here, or in parentheses is kilojoules. So either one of those values would suffice as long as you use the same units when you doing your calculations. So let me show you a reaction, because it's always better to have some type of application. So here's one of the examples we did in class the other day, where you had the hydroxyl group coming in to attack carbon, and then the iodine leaving to do a substitution reaction. And so these are the two products, where here's my cyclohexane ring with OH substituted, and then here's my iodine that left. So the question is, which bonds were broken? Well, we broke a carbon iodine bond according to this arrow, and then we made, according to this arrow, a carbon oxygen bond. So the carbon iodine bond from the chart takes 213 kilojoules per mole to break that bond, and then the carbon oxygen bond, so 367 kilojoules per mole of energy is given off when the carbon oxygen bond is made. So how do we calculate delta H? Well, it's a simple calculation. You take the bonds broken, you subtract from that the bonds formed, and then you get delta H, enthalpy. So delta H in this case is 213, which is bonds broken, minus 367, which is bonds formed, to give me negative 154. Anytime you have a negative delta H, we talked about this in the previous video, that reaction is going to be exothermic. And an exothermic reaction is always favored because it does not absorb energy, it gives off energy. And so if you remember this simple mnemonic, BBBF, or 3 B's and 1 F, is a bad report card. And that's the way you remember how to calculate delta H, bonds broken minus bonds formed. And let's take this and connect it with the energy diagram. So we know that delta H is negative 154. Here's the reaction again, and so my reactants are here, and then these are the products that are here. Now let's see what happens when we take this reaction and use a reaction energy diagram to describe it. So you see the reactants are disappearing, the products are forming. Here's the transition state. And then the difference in energy between reactants and products is delta G. Because this is exothermic, if you subtract the energy of the reactants from the energy of the product, you should get a negative number for delta G. So here, if you remember this equation, delta G equals delta H minus T delta S. So we've calculated delta H. If we ignore the entropy, then delta H and delta G are roughly equivalent. So from this information, calculating delta H, we know that delta G is about the same amount, or the same value. We also know that KEQ is greater than 1, because the way you calculate KEQ is products over reactants. And so if the reactants are really small and the products are large, then when you divide those two numbers, you should get a number that's greater than 1 for KEQ. All these things point to the fact that this is a highly exothermic reaction. So let's do another example. If you look at this reaction, again, this is a reaction we did in class, where the hydroxyl group is doing a proton transfer by deprotonating this site. These electrons come here to make a double bond, and then the carbon bromine bond gets broken. So these are my products, where you have a double bond, you have water that came from the OH here doing a proton transfer or deprotonation at this site, and then the bromine leaves as Br minus. So when we ask which bonds are broken, we broke a carbon bromine bond here. That cost 285 kilojoules per mole. And then we also broke a carbon hydrogen bond here, which cost 414 kilojoules per mole. Which bonds got formed? Well, we made an OH bond here to make water on in the product side. So the OH bond, making that gives off about 464 kilojoules per mole of energy. And then we also made a carbon-carbon double bond, which gives off about 611 kilojoules per mole. So how do we calculate delta H? Well, if you break more than one bond or you break multiple bonds, then you have to take the sum of the energy value. So delta H in this case is the sum of the bonds broken minus the sum of the bonds formed. If you look down here, the bonds broken again were 285 and 414. So we add those two numbers together to get 699. If you look here, the sum is 611 plus 464. Add that to get 1075. The difference is negative 376 kilojoules per mole. That's delta H. Again, you have to take the sum if you break multiple bonds or if you form multiple bonds and doing this reaction. So let's connect this with the energy diagram. So here again, the reactants are going to disappear, the products are going to form, and then going from reactants to product, we always go through a transition state. And so let's look at again how we calculated delta H. The sum of the bonds broken, which was here, sum of bonds formed, which is here, and then the overall delta H is negative 376. What does that tell us about this reaction? Well, we know delta G is roughly the same if we ignore the contribution from entropy. And we also know that KEQ again is going to be greater than 1 because delta H is a negative value. All of these things point to again this reaction being highly exothermic. So now let's talk for 1 second about transition states. Again, same reaction. What is a transition state? We talked about it in the last video. It's the highest energy point on the energy diagram. And in the transition state, you have partially broken bonds and partially formed bonds. So let's take this same reaction and let's look at it in terms of the energy diagram. So here are my reactants. And again, as the reactants disappear, products are forming. And then at the very top of the energy diagram is what I call a transition state. So these are either partially broken or partially formed bonds. So remember, to get water down here, you have to have a partially formed bond between O and H in the transition state. To get this double bond in place, there's a partially formed bond between this carbon and this carbon. This carbon hydrogen bond is partially broken. We also broke the carbon bromine bond, so that's partially broken. So the transition state looks like this, where all of these dashed lines simply mean that these bonds are either partially formed or partially broken. Right, so here, this is a chance for you to do some work also. I gave you the bonds broken and the bonds formed and the amounts of the energy amounts. You need to draw the products. You also need to calculate delta H and answer the question, is this reaction endothermic or is it exothermic? The same thing for this second reaction down here. Draw the products, calculate delta H, and then answer the question whether or not the reaction is endothermic or if it's exothermic. Alright, so the last thing I want to mention is stepwise reactions. And what does it mean to be stepwise? Again, if a reaction is concerted, it happens all at once. If it's stepwise, there's more than one step in the mechanism. And so when you look at this reaction, you take this alcohol plus HCl, and then the alcohol gets substituted by chlorine. And so this, when you look at it, it looks like a simple reaction, but it's actually more than one step to get to the product. So here's my alcohol, and the first step of the reaction, the hydroxyl group is going to deprotonate HCl. You're also going to break the HCl bond, and then that's going to give me this, where now I have the alcohol protonated and it becomes water, and now it'll leave. And so let's look at what happens next. So the next step is the loss of water. You can see this arrow saying that I'm breaking the carbon oxygen bond. Those electrons are leaving with oxygen. So what do we get next? We have a carbocation here, right, plus the water that left from here, and then chlorine is still here because this is what has to react with carbon in order to get the product. So the next step is for chlorine to attack the carbon, and then we have the product shown here. So to go from here to here, that's one step. To go from here to here, that's a second step. And then to go from here to the product is a third step. And so the question that I want to ask is, what would the energy diagram look like for a reaction that has more than one step? And so let's look at it. So here are my reactants, and my reactants, the first step in the reaction, I go from here to here. This will be considered what we call an intermediate. It's not the product, it's an intermediate before you get to the product. And so the intermediate is here, but that's not the final step. That's only the first step in the reaction, right? In the second step, the intermediate gets converted into this carbocation, because if you remember, the next thing that happened was that water took these electrons and left. So this is also an intermediate. And then from here, this is where we got where we formed the product from. So when chlorine attacked here, we got the product. So the next step would be for chlorine to attack, and so this intermediate gets converted into the product. So that's each one of these humps in this diagram represents a step. So at the top of each hump you have a transition state. In between two humps you have your intermediates. So you went from reactants to intermediate, and then this intermediate got converted into a second intermediate, and that intermediate got converted into product. Every step in a reaction produces a hump in the energy diagram. So if a reaction has 5 steps, then it's going to be represented by an energy diagram with 5 humps, right? This particular reaction had 3 steps, so we went through 3 transition states, but we also formed 2 intermediates.